It might be surprising to learn, but learning more about the periodic table can help us understand a wide variety of things, such as arsenic poisoning. For example, the reason we're worried about this is the arsenic poisoning kills approximately 43,000 people a year, which I did not realize it was still quite as common. I knew it was something that killed people, but I did not realize it was much until I did some research for this, actually. In addition to this, nearly 200 million people across the globe are exposed to dangerous levels of arsenic from sources such as their drinking water and food. One of the mechanisms for the toxicity of arsenic is that of the element involved in a compound containing arsenic replaces a compound containing phosphorus in the body. This manages to interrupt multiple important steps in glycolysis, in addition to a few other mechanisms that can be related to its lethality. So a question that might be reasonable to ask is that what does this have to do with the structure of the periodic table? Well, in this chapter, what we will explore is why is it that phosphorus and arsenic have very similar properties, and because of that, it becomes possible for one of them to replace the other and to function as a poison in the body. So it turns out this is actually related to the structure of the periodic table. It gives us some information that helps predict an effect like this. So to make sure we know what we're talking about, this is the example. This is what the modern periodic table looks like. So if you've seen this document before, here's what we're talking about. We'll talk about all the parts of this. If you don't know what some of these numbers or labels mean yet, that's okay. We'll be exploring this in this chapter. I just want to make sure when I say the word periodic table that we're all talking at the same thing. You've probably seen this in our classroom before, for example. We've got one up on the wall. I'm pretty sure there's two actually in the room I'm currently teaching in. So the periodic table. First, we need to go over some terminology. This is so we can talk about the things that we just saw. So first off, just to be able to talk about it, the rows of the periodic table are called periods. So that's the part that goes across. The columns of the periodic table are referred to as groups. This is the terminology I will use throughout my class. In case you see this in material from other classes or maybe online, you may also see them sometimes called families. We're referring to the same things here. But for my class, I'm going to exclusively call them groups. There are three main classifications for the elements in the periodic table. Every element, every single one, falls into one of these categories. Metals, nonmetals, and metalloids that occur somewhere between the two. We'll be talking about these later throughout the chapter, but this is just to introduce you to some of the groupings. In addition to this, the three groups can also be split up based on their location. We have the main group elements, and then the transition elements, which also include the intertransition elements. So let's look at our periodic table now and find out where all these groups are. And then as we go throughout the chapter, we're going to talk about what's different about these groups and why we care about these classifications, because just giving a name by themselves isn't that useful. So looking at our document here, first let's talk about metals versus nonmetals versus metalloids. So metals occur on the left side of the table. So metals on the left. Our nonmetals occur on the right. And then what we have is you'll see this dark black line here that I'm going to make red. This line is what separates us, the metals and the nonmetals. Any element that lies directly on this line is considered a metalloid. For example, arsenic here, AS, one of the ones we were talking about, that would be a metalloid. Silicon here, Si, you could call it that. Note, I will mention that depending on what you're reading, a few things will mention some exceptions, that a few of these are more just metal or just non-metal, the most prominent being that aluminum functions entirely as a metal. For any assessment I am doing with you, I'm not going to directly question on that. Is aluminum a metal or a metalloid? I don't think that's useful. The main goal is that this dividing line is the line between the metals and the nonmetals, and the things right on the line have some behaviors that act like both, and so they are considered metalloids. So for that reason, I'm not going to try to trip you up on the one or two that you might be able to define as just metal or just non-metal. You may also notice that this means that significantly more of our elements are metals because there are way more on the left side than there are on the right. That is a true statement. Most elements are metals, some are non-metals, and then a handful can behave as either metals or non-metals. We call those metalloids. So that's one way to break everything up. The second way is already identified on this figure. You'll notice that the main group elements are in yellow. So that'll be group 1A and 2A, the ones on the left, and then the groups on the right, which we labeled as 3A, 4A, 5A, 6A, 7A, 8A. The reason we call these main group elements is because they're especially predictable based on something we're going to talk about in a few slides called their number of valence electrons. So their behaviors are going to follow some predictable patterns that will help us be able to make some use of that information. When we learn about those patterns, it's less easy to follow those trends when we get towards the transition elements, which are the ones that occur in the middle. You'll also notice this thing called the inner transition elements. The way to understand this is, so this little blue arrow here pointing, these elements right here, all of these behave like they go in this little itty bitty blank part right here of the periodic table. This is important because sometimes it can be non-obvious if you haven't looked at one of these things before and nobody's ever pointed it out to you. It might just look like, oh, there are these other elements that just go in the bottom and they're somehow related. The reason for this is just that it would make the table incredibly long if we tried to stick them in right there, but they behave like they're in periods 6 and 7. So when we start talking about behaviors related to periods and to groups, we're going to treat them like they're in that part of the periodic table. It's just the periodic table would extend so far that it would become more difficult to use. So for convenience sake, we put them down below, and people were expected to understand, oh, they act like they're in that little spot right there. And that it's kind of like there's another, like, see this indentation I'm circling right now? How there's this blank spot here that periods 2 and 3 don't fill, but then starting in 4, we have the transition elements. It's like you have a second one of those once you get down to periods 6 and 7. And again, we'll talk about why as we start to look at how we label electrons and where those electrons go using the concepts from the last chapter about electron configurations. Okay, that is all I want to do in this one. This introduces us to the basics of the periodic table and the labels. For the next video, we will start working on the concept of electron spin, but I'm going to end this here.